Howdy. Let's give it a moment or two. So today I'm going to work through more LeetCode questions for about an hour. I am exhausted. I'm so tired, but I think I can get a few questions in short period of time. And I think the plan is going to be to do a few problems. Probably get to sleep. Let me just see. Oops. Let me just see what the stream looks like before I begin. Looks okay from that perspective. How about the other one? Let's see. Just give it a moment. Oh, I'm so tired. It's already like a minute in too. All right, hello. Let's see. Just give it a moment. Yeah, it seems okay. It's not very loud, but it's okay. It doesn't need to be super loud. All right. Let's pick a question. Indices with opposite parity. Okay. Yeah, I'm gonna fall asleep now. Nouns of length n, score an index, defines the number of indices j, such that I is less than j is less than n. Okay, and nums of I and nums of j have different parity. One is even and the other is odd. So the numbers to the right that are odd or even, I think. So score. So we could just go right to left, count the number of odds, count the number of evens, and we write into the array the opposite parity of whatever number we're looking at. And we write before we increment. So we could say odd, 0, even, 0, 4, and I think we go back to front. And we could even actually return the same vector. So we would say, we'll do it this, or actually I could do it this way. So x is either odd or x is even, depending on check. Yeah. Odd plus equals check. Plus equals not check. So if it's odd, we're gonna check the even values. It's even, check the odd values. We use the odd values. I think it's that simple. Let's see how we do here. Wrong. Oh, it's gotta be the way around. Oops. Actually, there's something important here. Auto pointer equals r nums.rb. I forgot, I gotta go backwards. It's still very similar to this. I don't know, I could do this. No, okay, never mind. Never mind. Just could still use iterators, but just have to use this a little bit more correctly, I guess. I'm just gonna go for it. I think this is correct. I'm very tired. There we go. 100%. Yeah, it's about as good as you could do it. That's kind of a simple question. We've already done this one. I was gonna explain the ones that I've already done, but I'm not gonna do that today. I'm kind of tired. I'm really tired. I'm exhausted. I'm like ready to fall asleep. Binary tree from descriptions. 2D integer array descriptions of I indicates that the parent is the parent of child in a binary tree of unique values. So it's parent, child. I guess his left is left child, the right child is left, and child's left child. Yeah. Okay. Construct the binary tree described by descriptions returns root. Oh, that's interesting. Generated such that the binary tree is valid. I like this. It's a cool question. I like this a lot. The root node has no parent. Do I just need to? I need to just construct the tree though. Okay. I was gonna say, can I just return the root node? They give me. I think I'm not gonna. I'm not gonna use smart pointers or anything for this. I'm just gonna use raw tree nodes. Yeah. Okay. I don't know if they need to be on the heap though. They probably need to be on the heap. I'm gonna put them on the heap. Yeah. All right. Do they have numbers associated with them? Let's see the constraints. 10,000. Okay, it's between 1 and 100,000. It's valid. Parents of I is the parent. Yeah, so the integers are actually the values in the nodes rather than. Okay, that's interesting. These need to be unique values. Otherwise, it becomes ambiguous. Okay, that's peculiar, but all right, that's fine. Yeah, there's some caveats to this to work properly, but that's okay. So we're gonna have a static nodes 1001 initially empty. And we're gonna say for descriptions. I actually don't want ints here. I want tree nodes, pointers. Interesting. Huh. Okay. Maybe. Okay. We're gonna say parent 0, child 1, principal left child is gonna be 2. Right. So if nodes of parent node think we can do it this way. And we're going to say the child. Parent node, child node, and then we can say if left parent node left equals child node else. And we would normally, for both of these, it's not a bad idea to initialize the variables that you're using. It's not necessary to do this, but it's a kind of a good practice to do it like this. What did I do? I don't know what I just did there. I'm supposed to copy paste this, but yeah, this is probably not necessary to do all this extra boilerplate code, but it's kind of good practice to put it in there anyway. So we'll create the parent if it's not there, create the child if it's not there, and then we'll assign the parent, the child, and the parent. Okay, that seems. And deallocation, it's going to be very similar. So that's allocating the memory. Deallocating the memory is going to be, I'm going to write that code now. There's more to this, I think, but we're going to write that code now. Oh, I want to return this, but deallocate. Oh, okay. Oh, that's really awkward, huh? I guess I could create a. Oh, this is really awkward. Oh. The problem I'm running into is I want to return the binary tree and then I want to delete it for the next iteration. The issue there is I want to return and have it checked, but also delete it afterwards. Oh, that's very awkward, huh? Huh. I mean, I could clear it. Okay. Yeah, okay. I won't be able to do it the way I like to do it. Because I kind of need this structure to exist before I oh, we also need one more thing here. Has parent. I want to figure out which one doesn't have a parent. That's also subtle. I need to get the root node. Trying to think if there's like an easier way to figure out which one's the root node. Basically, the node that doesn't have a parent, it's never a child. Every node will be a child at some point except for one. Is there an easy way to find that one? Okay, we'll do this one. We'll just keep it simple. We'll just keep it simple. We'll do a simple search. Root node is root. This one can be done with a simple second pass. That one's fine. This one's a little more complex. Actually, no, that's not. Well, I'm actually not doing this correctly. No, I'm not. I'm not sure if they should always be true or always be false. If it's a parent, we should set that to true. And then if it's a child, we should set it to false. The child we could always just end with false. So if it's true or false, it'll still be false. But for the parent, if I end it with true, it'll still be false. If I or it with true, the problem with that is it'll reset, which is not really what I want. I could do is parent and is parent and is child is probably better, or just is parent and is child. Seems bad. And they're just always false. All right, let's try this. This maybe is better. So there's some logic I can use with this, which might be helpful. It's ended up being a little more complicated than I thought it would be. So if is parent of parent and not its child parent. And the root is the parent, and we can break. Oh no, actually I don't want to break. So this won't work either if I do it like this. This is going to give me problems. I need to, I think I need to do do it twice. Do the search and also to deallocate, which is pretty awkward. Let's try to avoid that. And on the other side, also these are nodes. Very awkward, huh? Yeah, I gotta deallocate this memory. It's pretty confusing. Something like this. Hello, buddy. Do you want for me to like your video? Wait a sec, you were coding in a vehicle. What's up, Adarsh Prajapati? Hope your day's going well. Welcome, welcome. Coding in my home. Coding in my home. But what's up, man? What's up, man? Some compiler errors here. I'm so tired. It was not a long day at work. I just had a hard time sleeping. Give me 1 second. Okay, so I got a wrong answer. I didn't really explain all of what I was thinking there. I kind of wanted to code it before I explained it. But it's a bit involved. I was hoping to maybe try to optimize this a little bit, but it's not so easy to do. Let me see if let me see the constraints again. I was kind of preemptively optimizing a little bit, which is probably not good. 10,000. Okay, so it's not too many nodes to work with. This will kind of be on the slower side. This part. Yeah, this is not great. Not ideal. Okay, so I maybe could have a. No, I don't know. I was wondering if maybe I should put in a static. I was wondering if maybe I should put in static memory the previous vector for the descriptions. But I'd have to copy that if I did that. I don't know if that's a good idea. I could maybe copy it here and then move it, but that seems bad. I don't know. That would allow me to use a more dynamic approach to clearing the static memory before I started using it again. I'm not so sure. So anyway, Okay. Um, huh, that's incorrect. 0, 0, 0, 0. Okay. I think I need to set the value. Yeah, I forgot to do that. Okay. So I guess I do need some of this code here. But I don't think this isn't quite working the way I would expect it to. Even with, yeah, because I'm missing some elements here. So if the parent doesn't exist, we create it. If the child doesn't exist, we create it. And then if they do already exist, we just set them to these pointers. And the child node is going to be on the left side or the right side. Hmm. Hmm. I think I got the root correct. 50, yeah. I don't know why, I'm so tired. I don't know why. I don't know why this is incorrect. Hmm. Hmm. Oh, that's why I've left. Okay. That's why. I should have gotten a I don't know what this maybe is list.left or something. I'm not sure what happened here. But this should be, pretty sure I should get a compiler there or something. Something weird going on there. I'd have to check and see what happened. I'm not Mr. Beast to do any $10K super chat, but yeah, I can make sure to like. I appreciate that. Thank you. Thank you. Okay, bye. Nice guy. We'll meet again when the Earth collapses and you don't work out like your street. Okay. Thanks, man. It's good to see your dedication. What's up? Herman Singh, Heman Singh Kandari, Hemant Singh Kandari. What's up, man? Howdy. Thank you. I appreciate that. Yeah, some level of dedication. Now, here's a question. If this wasn't, what was this pointing to? If it probably should have been like left child. What was this referring to if not child left? What was this referring to? Maybe this left or something? I don't know. I was expecting this would give me some kind of compiler error. I don't know why. This apparently didn't need a... it didn't... I don't know how the compiler didn't catch that. Maybe that had something to do with... There's something something there I'm not aware of. I'm going to try this and see how it goes. This may or may not be correct. I think it's correct, but we'll try it. We'll see what I get. Oh, okay, it's worked. All right, that's good. It's probably not going to be that fast. Oh, it's very fast. Okay, it's one of the fastest. That's pretty good. Yeah, I tried to make it reasonably fast. There's probably some optimizations in there. Let me see something here. So, how are we doing on time? Also, how are we doing on stream health? Okay, stream health is maybe not the best. Let's see. There's something I wanted to see here. I wanted to ask this AI why this compiled despite using left instead of left child. I'm looking for something. Oh yeah. The bit rate's okay. About 30 minutes in. So what I wanted to ask is, okay, what was the feedback from the AI? Also, was this the fastest? It was pretty close to the fastest. Attempts, but has a critical flaws. Okay, thread safety, efficiency, potential logic errors. Okay, unsafe use. Okay, race condition. Oh, actually, there was something I wanted to throw in here. Let me see if I can go. Ready for this? There actually is something I can do to optimize this a little bit more and maybe get 100%. Let's see. Let's go. Let's see if I can find it. Practice history. Okay, not this one, not this one. It could be this one or this one. I have to check which one it is. I think it's this one. I'm trying to find some code that I wrote that I could add here. I shouldn't memorize it really. It's all right, you ready? It's gonna be const static auto fast IO. It's going to be an immediately invoked lambda expression. It's going to be stood sync with stood.io false. And I think it's stood iOS. And then it's also stood cn dot something null pointer tie. So we're gonna tie let me see, is it here? iOS sync with stood.io. I think it's this. I think it's exactly the right one. Did it from memory. Const static, auto static, const auto. Maybe static const auto is better. Is this the same? I think that's right. Yeah. So this maybe could speed things up a bit. Okay, it's saying race condition, multi-thread environment, corrupt the shared state, common among online judges. I don't think it's multi-thread. I don't think it's how it works. Runs multiple test cases in the same process that restarting data from previous test case will remain. This cleanup loop runs before processing the input. The input is a disjoint set. Cleanup might work, but logic is fragile. It's not thread safe, but it's not intended to be thread safe. Every single time that's actually created. Clean up. Okay. Logic flaw and root finding. Loop to find the root. Iterates over descriptions again. Yes. What did I say if I submit this? Oh, generally correct for finding node as a parent but never a child, relying on the order of descriptions to break early is fine. Dependency be perfectly reset as high. Refactor local unordered map or local vector size dynamically or fixed but non-static. Thread safety and constant initialization. Okay, so it's just thread safety. Okay. The root finding of maybe I did make a slight error there. Oh no, so it's faster than the most, but it's not actually the fastest. Okay, I did make it faster though to add this extra piece of code. Yeah, okay. Yeah, I don't think they do the test cases in parallel. I don't think it's how it goes. Cleanup loop, specific micro optimizations. Okay. Generation counter. Generation ID. Oh, interesting. Oh. Huh. Oh, can use generation ID. Yeah, of course. I mean, this is of course not gonna have to delete, we have to clear the memory or deallocate the memory or recycle. So I could recycle the objects. That's a good idea. Let's try that. Let's try object recycling, see how that goes. So there's a generation. Okay. And we're going to say plus generation ID. So we're not going to clear the memory. And we're going to say if not node's parent, then we create this node here. Um, generation parent equals generation ID. Then we're going to do that tree node parent or temp nodes parent left, right. Is the parent, and I think that's it. We do the same thing for parent, child. If it doesn't exist, then we create it. Check the generation ID. Okay, very interesting. The same thing for the child. I like this approach. I think this is cool. So parent node is parent. Child node child. So this is the same. This parent is child. Finding the root node, I'll have to come back to that. I'm not sure if this is the best way to do it. Okay, let's try this. What's up, chat? Hi, what's up, Zen? What's up, Rohit Shekawaturko? Hey, buddy, I've just started learning Python. Do you have some tips for me? What's up? Dude, go hard, man. That's my tips for Python. Go hard, dude. I don't know. Python's kind of weird. Python has a lot of, okay, let's see if this works. Let's see if it's correct. Python has a lot of, there's a lot more to it than people realize. Like, you can kind of get, like, from 0, oh, here we go. That's a lot faster. That's almost 100%. That's way better. You can go from, before it was 58 milliseconds. Now it's like a third of the time. You can go from you can go from not knowing really anything about Python to being able to do things with Python fairly quickly. Like, it's a very straightforward syntax in a lot of ways. It's also very, excuse me. It's a very straightforward syntax in a lot of ways. The simpler parts and it's a very what's the word? I guess you could, like, if you had 5 levels, you can go from 1 to 2 very quickly, but going from 2 to 3 to 4 to 5 in Python is actually pretty tough. The reason is that Python is actually like very complex when you go deeper into it. But the syntax is very straightforward. It's very expressive. It's very terse. You can kind of get pretty far pretty quickly. But when you want to start going deep into Python, it starts to get quite frankly, pretty wacky. Python's a very odd kind of language overall. It's considered to be very easy, but I wouldn't say that's like totally accurate. It's actually, the harder aspects of Python are very hard, but the easier aspects are much easier. So this kind of has this like weird distribution where it's like it's pretty easy early on. It's like much easier than other languages really early, and then it's like much harder than other languages when you get to the harder stuff. So that's kind of how I would express it about Python. It's like it's not as like the learning curve isn't as linear. It's like it's very easy, very very early on. You get really far really quick. I guess this would be sort of this kind of curve, and then it gets like pretty hard after that. It gets like really hard to get more stuff about Python. Gets pretty. I don't know. It gets very strange, involved. I guess a lot of most scripting languages are like that, where it's like very front loaded, where you can do a lot really quickly, easily. But when you start to get to more complex things, it just gets way more involved and way more complex and a lot very detailed, a lot more nuance and subtleties and things. I mean, I don't know if that's compared to C++. I mean, C++ is like complicated the whole way through. But you can do things more easily in C++ that are more complex things can be done more easily in C++, something like that. And it tends to be a little bit more efficient too. So yeah, but yeah, do go hard. It's like my only advice is like just keep going. That's also, I guess, one thing I could say about programming languages is that it's not so much the language that you're using as much as it is your proficiency with that language. So the more proficient you are with a particular language, like the easier it is going to be to use it and to not make mistakes. Because a lot of people like to try to like make a new language, or like they do all this weird stuff, and some people will try to rag on a particular language being really bad for some reason, but they all have their like pros and cons and quirks and ecosystems and libraries and all kinds of stuff going on, that it really does come down to like how proficient you are with that language. There are some things that are going to be harder depending on the language you're using. That mostly revolves around like the libraries that are available. I have learned that the hard way, that like, yeah, there's some things that they just don't really have easy libraries available for certain things, and you could write one your own, but it's gonna take a lot longer, and like if you don't want to spend the time, then you might be better off using a different language. Like there are things I do in Python from time to time just because it's easier to get it done quickly, because of the libraries that are available. 2 inefficiencies of prevent it being truly micro-optimized. Okay. Redundant cleanup loops. Twice at the end. Find root reset flags. Use a generation ID for his child and his parent if needed. This eliminates the need to manually reset the usability value raised to false. Only check. Oh, okay. Inefficient root finding. Root finding loop iterates over descriptions again. If the root node appears only as a parent in the first description, you find it quickly. If the root is the last unique parent, you still iterate the whole list. Optimization. Track the root candidate dynamically or iterate only over the unique nodes touched, but you implicitly know via the generation check. The biggest one is removing the Boolean reset loop. Refined micro-optimized code, a version that removes all linear cleanup loops, relying entirely on generation IDs for logic state recycling from memory. Okay, child gen, parent gen, node gen, current gen. Okay, so you do child gen and parent gen. All right, but how would we need a way to find the root without a separate cleanup. Track a potential root. A node is root if it's a parent and never a child. You can verify this at the end by checking generation IDs. That's not the easiest thing to do, though. I like how they did the triple. I should do that, actually. I should be doing that. Some of this is like easier said than done. This also could. Oh wait. Yeah. These also could be triple. Triple. Um. Um. I'm not sure if there's any benefit to doing this actually, to rewriting it this way. Double assignment is what I should call it. It's a triple, like name line of code, but a double assignment. It just kind of looks cool. I don't know. I don't know if this is a good like coding practice. It's probably not. It's probably better to do it the way I've been doing it, quite frankly. Let me just make sure this still works. But yeah, there's Python there's a lot you can say about Python. Or generations instead of saying bools. Okay. Find root, iterate, descriptions again, unavoidable, but we remove the cleanup logic. Okay. Parent in this gen and not a child in this gen. Static definitions. I'm wondering if I could put maybe I could put the parents into a vector of parents. Would reserve could possibly vector of parents, static vector. Don't need to keep reallocating for it. Is that when I say parent, keep the same. I don't know. I don't know if I need to do that. Never mind. There's no bunch of this. No here. No, it doesn't help. Never mind. I think what they just showed is probably about as good as it gets. So let's do similarly. Parent gen and child gen. I think they're right. Okay, we're gonna say parent gen, child gen is gonna be, oops, child gen. Generation ID. And then don't need this cleanup loop at all. We say we don't need the child either. We don't care. If parent gen parent is equal to generation ID and child gen is not equal to generation ID. Then we could set the root to the parent and break. Something like this. I think that probably is about as fast as I can go with this. Sleep man, it's 2:10 already. What's up, Hitmoo? Hope your day's going well. Welcome. I'm in the USA. USA. So my time is a little bit different. All right, I'm gonna. Although I am only gonna spend about 5 minutes more. I'm very tired. Okay, so that didn't make it much faster. Let's try again. The other one was still pretty fast. No, it's actually a little bit slower at points. Wondering if switching from bools to ints actually hurt performance. Granted, cleanup slow. Working with bools, it's probably faster. What do you think? Yeah, actually, I don't think. I don't know if that change actually improved things or not. Even though I got rid of the loop, bit sets so much, or potentially so much faster. Yeah, it's slower. It's substantially slower now. Let's try one more. Absolutely correct. Likely hurt performance slightly. How you use them, very valid. 1 byte per element. And array uses 4 bytes. Int will be slower due to cache misses. Ooh, okay. Is child flag into the same integer as the generation ID if you have spare bits? Or simply stick with ints? Huh. Huh. Simplicity and loop elimination are the dominant performance factors here. Stick with int for the generation IDs, arrays. Cleanup avoidance is more valuable. I don't know, man. That's not. That's not result I'm getting. I think the extra cache misses. Could be the cache misses. Yeah, it's like a lot slower. It's actually substantially slower. This is like twice as slow. This takes twice as long. I don't know, man. Let's go back. Okay, does this still work? I'm not sure if this code's still going to work correctly. Oh, that's about the same speed, actually. Let me try one more time. So, interestingly, This is a little bit faster, yeah. This is a little bit faster. It's not quite 100%, but it's faster. I think it's faster due to the cache. Due to caching. Try one more to see what we get. Oh, I'm not doing any delete calls because I'm recycling completely. Not deleting nodes. No, I don't need to delete the nodes. Good luck squeezing out those last milliseconds. Yeah, the fastest. Yeah. The pools plus gen ID. Fully recycle. Tree nodes. Seems very fast. 16 milliseconds. Sweet. Eating 99 solutions. Can't seem to get lost. 0.15. And 6 like cause the boss reset is fully almost completely mostly in cache. Doesn't cost much. It's using ins for the parent check. Does still incur extra costs. Loop is on mute. Basically, the loop is really fast because the values are in cache. Yeah. Yeah. 12 to 14 milliseconds, okay. Input access and branch prediction. Only strictly needed as child. The node is the root. If it never appears as child, can track the. Oh. Oh. Can sometimes mispredict. Point to remember arithmetic to select the child pointer without a branch. Huh. Optimize the if wells to test this. Never called delete. Yeah, I don't. God mode snippet. No is parent. Oh, I didn't think of that. It's clever. That's probably what I'm missing. I don't need his parent. They're all just parents. Okay. Aha. That does speed things up a bit. Yeah, it's redundant there. It's already a parent. I didn't even think about that. If it's not a child, then we've got it. Okay. I don't care if it's a parent. We know it's a parent. All right. We also don't need to do these. Only really care about the parents, but not the parents' child. Oh, that's very interesting. Huh? Okay, let's try this. I didn't even think about that. That was a good catch. Oh no, not his parents. Should be his child down here. Yeah, if we're only looking at the parents anyway, then we don't have to check if it's a parent or not. That's kind of obvious. No! Oh, I got destroyed. I got destroyed. No! I was doing so well too. I messed up the code too much. I messed with the code too much. It's not good. Okay, hold on. What did I do wrong? Whoops. Okay. Huh. All right, what does it say? It says index -1 out of bounds. Uh-oh. Uh-oh. Oh, never found the parent. Hmm. Oh, wait a minute, but there are some issues here, right? I need to set the children and I need to set both of these to false. I have to set both of these to false. During the cleanup. I think that might be what's going wrong. That's kind of subtle. Whoops. Okay, let's try it again. It could be wrong again. There could be something subtle there that I don't realize. But let's see. Okay, we got it. All right, that's a subtle thing. Okay, it's still about the same speed anyway. Dang. Excuse me. Oh, 9 milliseconds. Ooh, that's really good. Okay, it's not 100%, but it's still really good. Okay, here we go. This one got me 9 milliseconds. Okay, let's try one more time. I'm gonna check the fastest solution, see what I get. Okay. Hmm. Input access and branch prediction. Flatten input access, remove vector overhead. Using the raw pointers, help the compiler optimize better. Inside the loop, try iterating with pointers. Okay, branchless linking might mispredict on random tree structures. Pointer to member arithmetic, it probably doesn't. Second cleanup. Optional risk. Could change the check. I don't really want to. Current risk set is fast, safer, and likely fast enough. Yeah. And often just server load variance. Memory page alignment lock rather than code logic. Object pool with generation tracking. It's pretty cool. But I do want something here. I do want to try this. It's pretty fast as it is. Could use a pointer instead. Or yeah, an iterator instead. this to description. Very slight optimization here. Micro optimization span. So there is instead of using indices, there is a slight optimization here. That's kind of interesting. Does make it a little bit faster. Using iterators. Oops. So it was only going to be a few minutes here, but I ended up spending several minutes while working on this. Okay. Yeah, basically use this for the other loops too. Only need the parent though for this one. And this one can parent child. This should be a little bit faster, slightly. Not much, but slightly faster. 9 milliseconds is pretty good. No. All right. We'll try one more here. I think I'm going to do one more, and then I'm going to check the fastest solution, see what they had. I was so close. So close to the fastest. No. Come on. Why is it so slow now? What's going on? I think that actually slowed it down. Range-based for loops. Two iterators and may have selections. It seems to be going a lot slower now. Several milliseconds slower. Huh. I'll try one more time. Let's see what I get. Switching to explicit iterators likely slowed you down because modern compilers optimize range-based for loops extremely aggressively, often generating identical or even superior assembly compared to manual iterator loops. Range-based loops are often faster. Compiler optimization. C++ standard defines range-based loops in a way that allows the compiler to cache end, eliminate redundancy, completely unroll a vectorized loop because the bounds are known to be invariant, simplify logic, avoids potential human errors in manual iterator management, forgetting to cache end or using post increment instead of pre-increment. This is pretty funny. There were like several videos and discussions about pre and post increment. When you write manual iterators, you risk uncached end. Naive compiler might call end of iteration. Post increment creates a temporary copy of the iterator adding overhead. Range-based loops implicitly use the most efficient increment. Instruction bloat. Manual loops sometimes prevent the compiler from applying certain loop unrolling and vectorization optimizations due to perceived complexity. Okay. Extra layer of indirection the compiler must resolve. Usually optimized away, tight loops and small bodies. Extra dereference can inhibit some micro optimizations. Happy path, the compiler. Iterative version introduces just enough complexity to confuse the compiler, prevents specific CPU pipeline optimization, resulting in slowdown. But for a single-digit cycle counts per iteration, the range-based loop is more robust for the compiler. Interesting. So it's saying, go back. Dang. Who'd have thought? Who'd have thunk it? Who'd have thunk it? Yeah, I'm pretty surprised, actually. All right, let's try one more time. Jeez, man. Jeez. Oh. That didn't seem to help too much. We'll do one more. I'm going to look at the top solution and see what's different from what I did. I don't know. Okay. Anyway, these are my submissions. Oh, wait. It's over here. So 5 milliseconds. I was so close. I would need to be 4 milliseconds. So I got 9 milliseconds, which is pretty good. It's pretty good. Although it's not getting 9 milliseconds consistently. Okay, here we go. 5 milliseconds. What does it think? Yo, what's up, Varun? Varun Talreja. Welcome, howdy, hello, hello. All right, I'm going to try one more time my code. See what a number I get. And then we're going to see. Okay, highly optimized God tier solution that pushes C++ performance to its absolute limit, combines static storage pooling, zero dynamic allocation, and cache linear memory access to achieve near theoretical minimum runtime. Okay, so mine was 28 milliseconds, although I did get 9 milliseconds at one point. I should show that. I should show I got. Did get 9 milliseconds at one point. There it is. This one. Which I think is like the same code that I have right now. Excuse me. Oh, I think I understand. So didn't use dynamic allocations. Maybe that's the big difference. Cache linear memory access to achieve near theoretical minimum runtime. Okay. Pointers into this array, storage plus bound plus plus. Okay. Offset normalization, subtracting min v, it maps values 1 to 100,000 directly to array indices. Moves bounds checking overhead and simplifies indexing. S bound, okay, array are using generation IDs. Only resets the exact number of nodes used in the previous test case. Persists the count of used nodes from the last run, ensuring linear cleanup when this number of nodes in the next range. Root finding via parent pointers stores the parent index in parents of C equals P plus 1. Root is found by following the parent chain upwards. Clever way to find the ultimate ancestor without a separate boolean flag or second pass. The logic sets a candidate and a while loop results into the true root if that candidate was itself a child of someone else. Processed later. So the while loop might technically be redundant if the input order guarantees the root. Standard logic is The root is simply the node with parents roots. The while loop suggests a specific traversal strategy, but typically is tentatively branchless link use ternary operator. Comparison of previous versions, this version. Okay. PowerPoint walk. I think it's the heap allocations. I think the other ideas are better. Okay. All right, so we got to use a static array pool. How do they do that? Max v, min v, range. This min, this one. Excuse me. Tree node storage. Okay. Oh. Huh. Actually, I could really, all I need to do is just subtract this here. And then I don't need to do this anymore. Huh. Let's try this. I don't know actually. Let's go for this. It's correct. 8 milliseconds. Cool. I was kind of wondering about that too. I was like, maybe I could just do it this way. Oh, there we go. 4 milliseconds. Found it again. I got 4 milliseconds. Huzzah. Okay, we'll do one more. I'm pretty sure the last one was 5 milliseconds, so 4 milliseconds is supposed to be better than 100%. I think if I keep running it, I'll get down to 0 milliseconds. It's tied for it. Almost entirely due to server load and memory page alignment. Code logic, limited heap allocation, remove pointer indirection, minimize cleanup, optimize loops. The theoretical speed limit for this problem. Luck of the draw on the test server. Okay. I think that's it. 14 milliseconds. It's pretty fast. Nine milliseconds. Maybe it may not be the fastest actually. Maybe just slightly. Uh, 3 milliseconds. I did it. Oh, a screenshot. I did it. I did it. Did it. Got 3 milliseconds, which is one faster. 100% solutions. Woo! Hey! We did it! We did it! Hey! We beat everybody else. Everyone else in the world. I was gonna say, I'm like, I think this is probably optimal. Correct. I mean, there's a little bit of luck involved in terms of how fast it'll actually run. But, yeah. 0.01%. Sweet. Theoretical speed limit. Awesome. Awesome. It's algorithmic correctness, memory management, static object pools. The biggest change. It's the biggest one. Using cache locality, direct array access instead of pointers. Overhead reduction using gen IDs, eliminate cleanup loops. Compiler cooperation, sticking to range-based for loops to let the optimizer. Awesome. Static object pool plus generation tracking pattern. It's gold standard for high performance programming. Oh, 100% batch. Feels so good. It's good though. We did it. We did it. All right. Awesome. So that's cool. I mean, probably spent too much time on this question to be totally fair, but figuring out micro optimizations is not the simplest thing. It is a kind of a puzzle in its own right. That's pretty good. It's pretty good. I like it. So yeah, great. We're gonna submit one more time though. Submit one more time. So this one's probably not 100% again, but that's pretty cool. 3 milliseconds is, yeah, it's fast. It's fast. Does that mean if I go to look at the solutions now, I'm gonna see my solution here. That 3 milliseconds. No, I guess it's got to update, right? I'm still going to see someone else's solution. This one was 5. Mine was 3. Mine was even faster. That's cool, man. That's cool. All right. Cool. Cool. What do we do now? Let's stop here. Let's quit while we're ahead. So yeah, that's some good stuff, man. Got my 3 millisecond solution here. Freaking awesome. Let's quit while I'm ahead here. I think that's a good call. So yeah, thank you all for watching, coming by, saying hello. I do appreciate it. Ended up being an hour and a half instead of hour and a half instead of an hour. But yeah, it was good. It's good. So yeah, okay. I think I'll stop here. So yeah, thanks again for watching. Talk to you soon. Have a good rest of your day. And yeah, if you like the stream, don't forget to like what I do. Don't forget